Hi everybody, my name is Rafi Shabazian and I'm a Principal Cloud Network Architect for Oracle Cloud Infrastructure. In today's video, we're going to cover the features of our Dynamic Routing Gateway, also known as the DRG. We'll have a brief technical overview of the DRG components, followed by a workshop where we get to configure the components in the various ways and see how they interact with one another. Quick look at our safe harbor statement. Today's agenda is listed below. An overview of the Dynamic Routing Gateway, specifically what is the DRG, DRG route tables and VCN route tables and how they work with each other, route segmentation using DRG route distributions, how our DRG handles route conflicts, and an overview of equal cost multipathing feature within the DRG. Once we're done with that, we're going to build our DRG using the various components. We'll attach VCN, RPC, and IPSec attachments. We'll take a look at multiple route tables with multiple route distributions, and we'll implement a hub and spoke model. So what exactly is a dynamic routing gateway? A DRG acts as a virtual router. Essentially, it provides routing of traffic between your on-premise networks and your VCNs. It can also provide routing between VCNs within the same region or different regions by way of remote peering connections. A DRG uses different types of attachments to build the network topologies. And these attachments include VCNs, IPSec tunnels, virtual circuits, and remote peering connections. Each DRG has an associated DRG route table that's used to route packets entering the DRG to their next hop. And finally, each DRG route table has an associated distribution list to import destination routes. If we were to take a look at the topology on the right-hand side of the screen, the DRG, which is the main focal point, would be the big rectangle shape. Within the DRG, you'll have several DRG route tables. These DRG route tables will have corresponding route distributions. And by using these route distributions, we can selectively import the routes and CIDRs we want to a given DRG. DRG route tables. So a packet entering a DRG is routed using the DRG route table assigned to that attachment. You can assign the same route table to multiple attachments or create dedicated route tables for each attachment depending on what type of routing policies you want to achieve. When you create a DRG, by default, there's two route tables that get created for you. One where all VCN attachments will be associated with, and another one where all other attachments such as RPC, IPSec, or virtual circuits will be attached with. Keep in mind, a DRG route table is different than the VCN route table. So essentially a VCN has two different route tables. The DRG route table, which is used for traffic entering the DRG, and the VCN route table, which is used for traffic entering the VCN. The DRG route table and the VCN route table can be associated to each other as well, and this will be needed if we want to achieve transitive routing through the DRG. DRG route distributions. Distribution essentially is a list of statements that contain a match, such as an attachment type and an action. You can use route distributions to specify how route gets imported from a DRG attachment. We could have independent DRG route tables. Each has its own distribution, and each distribution may be importing from VCN A while the other one could import from VCN B, and so on and so forth. It's a way to segment and segregate traffic. DRG route tables support both static and dynamic routes. However, static routes are inserted into the tables manually, while dynamic routes are imported from attachments and inserted using the import route distribution. When a statement's criteria matches on an attachment, the routes associated with that attachment are dynamically imported into the DRG route table assigned with that specified route distribution. Likewise, if a statement is removed from the distribution, the routes are withdrawn from the DRG route tables. Continuing with route distributions, statements in a route distribution are always evaluated in a priority order. For example, the lowest number will always have the highest priority. The order of the statements which they're evaluated doesn't affect the preference set for the routes they import. And one thing to keep in mind when building route distribution statements, you can always create a statement which basically matches all attachments of all types. This, by the way, is the default statement for the auto-generated route table for all VCN attachments. DRG route conflicts. Static routes will always have a higher preference than dynamic routes. If there was a conflict between dynamic routes, the way they're resolved is first by analyzing the route's AS path. Routes with a source of VCN or static always have an empty AS path, while routes with a source of IPSec tunnel or virtual circuit will have AS path data. Otherwise, the attachment type that imported the route is evaluated according to the following priority based on the attachment type. So VCNs have precedence over virtual circuits, over IPSec tunnels, over remote peering connections. If we were to have two routes that had an identical network distance, the DRG is going to select the route with the highest priority. Again, static over VCNs over virtual circuits over IPSec. If two routes had the same route source, then the DRG is going to make an arbitrary but stable decision. So if we were to take a look at the screenshot within the slide below, we could see that the static route has taken precedence. However, if the static route was removed, then the dynamic route with the next hop attachment name of VCN2 would take precedence, followed by the IPSec tunnel to tunnel 1, followed by the RPC to Phoenix. ECMP. DRG supports equal cost multipathing, which is a flow-based load balancing network traffic over multiple fast connect circuits or IPSec tunnels. However, you can't have a mixture of these circuits. ECMP allows active load balancing and failover of network traffic between a maximum of 8 circuits. Oracle utilizes a 5-tuple hash, essentially the protocol, destination IP, source IP, destination port, and source port to distinguish flows for load balancing purposes. And ECMP is off by default. So if you want to enable it, you would have to go into the DRG route table and select Enable ECMP. Now, let's start using some of the components that we just discussed about to start building our own DRG with the various types of attachments with different types of DRG route tables and route distribution lists so we can see how traffic patterns are with each different configuration set. To start off with, we'll create a DRG and attach a couple of VCNs onto it. Once we do that, we'll attach a few more VCNs and we'll start taking a look at the DRG route tables. In this scenario, we're going to create 4 VCN attachments and terminate them into the same DRG route table. So here we are in the Oracle console. The first thing we want to do is go to Networking, under Customer Connectivity for Dynamic Routing Gateways. Now for the purposes of this video, I've already created 4 spoke VCNs and a hub VCN. So we'll just pick up from here where we're creating the DRG and we'll continue from there. We want to create a dynamic routing gateway and we'll give it a name. And for right now, we're just going to accept all the defaults. So under the advanced option, we get to assign some tags. Just click create. And here, it's going to go into a provisioning state. The menu to configure the DRG is located under the Resources section on the left-hand side of the console. In here, we are able to see the various things that we could do, and we will go into each one of these during the course of this video. The first thing we'll do is start creating some VCN attachments. We'll start creating 2 VCN attachments and take a look at the DRG route tables, the default ones that they're associated with, just to see what they look like. So let's go ahead and attach spoke VCN 1. And once again, under the advanced options, we're able to associate these with DRG route tables and VCN route tables. DRG route tables for right now, we're going to select the auto-generated DRG route tables for VCN attachments because this is the default DRG route table for the attachment type VCN attachments. We'll get into the VCN route table once we talk about the hub and spoke architecture, and that's primarily used for transitive purposes. So let's create this attachment. Let's go ahead and create the spoke VCN2 attachment. Select the appropriate spoke and click create. And once these report both in the lifecycle state of attached, we know that they're ready to be used to route traffic to and from each other. In this case, let's take a look at the rest of the columns so we know the VCN for each attachment is the respective VCN. We can see under the DRG route table that both of them by default got associated with the default route table for these VCN attachments. Here, we can actually view the details and further modify which DRG route table or VCN route table we want to associate these attachments with. For right now, we don't have any virtual circuit attachments or IPSec tunnel attachments or remote peering attachments. So we're going to go down to the DRG route tables and take a look at the auto-generated DRG route table for VCN attachments. Within here, we can click on the Get All Routes to look at the DRG route table and what it looks like. Since we have two VCNs attached, we should be learning both of the VCN CIDRs. And here we can see we have multiple subnets which are being learned from the two different individual VCNs. At this point, the DRG route tables know how to route to and from each other, since the default auto-generated route table uses a match all statement for its route distribution list. The auto-generated DRG route table for VCN attachments is associated with an import route distribution. This is the auto-generated import route distribution for all routes. If we were to take a look at this, we could see under the manage statements, we have a priority of 1 with a match type of match all, and basically no match criteria with an action of accept. This basically tells us we will import every single VCN's attachments, CIDRs, and subnets to this route table. Therefore, spoke VCN1 and spoke VCN2 should be able to route to each other. Let's go ahead and add a couple more VCNs to this route table. So we can just navigate towards the dynamic routing gateway details. Under the virtual cloud networks attachments, let's go ahead and click create attachment, spoke VCN3. And once again, spoke VCN4. Once spoke VCN3 and spoke VCN4 have been attached properly, we can go back to the DRG route tables for the auto-generated VCN attachments and see their CIDRs and subnets also be populated. So let's go back here, click on Get All Routes, and here we can see spokes VCN3 and spoke VCN4 are now a part of the DRG route table. So once all these VCNs are attached to the DRGs, and their subnets and CIDRs have been imported into the DRG route tables, we should then be able to have connectivity to and from each other. Let's go ahead to a couple of spoke instances that I have provisioned, and let's see what these pings look like. So on the left-hand side, we have VCN1 compute. On the right-hand side, we have VCN2 compute, both of them showing their IP addresses right at the top. Let's see if we can ping back and forth and what the behavior is going to be like. So ping 1.20. Notice it's not pinging, and ping 192.168.2.20, and this isn't pinging. And the reason why this is not pinging is because all we've done so far is configure the DRG route tables with the auto-generated DRG route distribution lists, and we have not yet modified the VCN route tables for each of these spoke VCNs to point their default route towards the DRG that they're currently attached with. In order to do this, we need to hop back over to the OCI console, and instead of configuring all of this within the dynamic routing gateway, what we need to do is go to each VCN independently and modify their VCN route tables to use the DRG as its next hop. So what we'll do is go under networking, VCNs, and we can go under VCN1, and I've already pre-configured a lot of this, and what we'll need to do is update the internal route table. Let's add a rule to use the dynamic routing gateway for the destination CIDR block 0000/0. Let's add this route rule. Let's do the same for spoke VCN2. Route tables, the internal route table. Let's add a route rule. Once again, target type of dynamic routing gateway with a quad 0. Let's add the route rule. Once these routes have been added, now the system should be able to ping each other. Let's go back to our screen and take a look, and there we can see that the pings have started responding. So I'm going to break out of these for right now, and we'll continue with the next step. Now that the spoke VCNs have been configured and attached to the DRG route table, we want to integrate a hub VCN so we can have traffic flow through the hub VCN towards the internet. In order to do this, the first thing we'll do is attach the hub VCN to the dynamic routing gateway. So we'll create the attachment for the hub VCN. And this will go into an attaching state. Once this is attached, we'll take a quick look at the DRG route tables for the auto-generated VCN attachments to see what this looks like. It's attached, so let's take a quick look. Get all routes. And notice we are now learning the hub VCN CIDRs and subnets as well. Let's take a quick look at our test compute instances to see if we now have traffic routing towards the internet. We'll do a simple ping to 8.8.8.8, ping 8.8.8.8, and notice neither one is working. The reason for this is there's still a little bit more work that needs to be done. We have to tell the DRG route table, in order to use the hub VCN, it needs to send the default route towards the hub VCN attachment. This is where the VCN route tables come into play for transitive routing purposes. Not only that, we're going to need to separate the hub VCN into its own route table and the spoke VCN into its own route table and import accordingly. So the spoke VCN needs to import from the hub VCN in order to know how to route the traffic towards the hub VCN, and the hub VCN will need to know how to import from the spoke VCNs so it could route traffic back to the spoke VCNs. Let's go ahead and take care of these configurations within the DRG. So let's close this window. Let's go back to the DRG. The first thing we'll do, let's create a separate DRG route table for the hub VCN. We'll call it hub VCN. Once again, we won't do anything under the advanced settings. We'll modify these manually as we go along. So let's create the DRG route table, and this is in a provisioning state. While this is coming up, let's go take care of our import route distributions. And within here, we're going to import the attachment for each VCN. So let's start off by adding the statements for each VCN. Finally, the last VCN. Let's create the import route distribution list. Let's go back to the route tables and let's associate these import lists with the corresponding DRG route tables. First thing we'll do is let's edit the hub VCN. And we want to enable import route distribution and specifically the hub VCN. And as we can see, we have CIDRs and subnets from spoke VCNs 1 through 4 listed in the hub VCN import list, DRG route table. Next, let's go to the hub VCN and associate it with the new hub VCN DRG route table that we just created. Under Advanced Options, let's select the hub VCN and click Save Changes here. And let's go take a look at the DRG route tables one more time. So, the DRG route tables for the hub VCN only know about the spoke VCN routes. And since we've left the spoke VCNs with the auto-generated default DRG route table for VCN attachments, we'll take a quick look at the routes over here. And here, we know how to get to the hub VCN as well as to all the other spokes. Let's take a quick look at our pings. Notice our pings are still not working. And there are a few reasons why this is not working. One, while we know how to route to the hub VCN, we don't know how to route to 8.8.8.8. In other words, the DRG route table associated with the spoke and the hub VCNs both don't have a default route associated with it. Two, let's assume we added static routes to the hub VCN and the spoke VCN, pointing the spoke VCN to the hub VCN and the hub VCN back to itself. This still wouldn't work because the hub VCN doesn't know which VCN route table to route towards. And three, we need to associate the DRG route table from the hub VCN to a VCN route table in the hub VCN, add the quad 0 route there, pointing it towards your third-party firewall, and that route, by way of association from the VCN route table to the DRG route table, will get propagated to the hub VCN and to the spoke VCN. So let's go ahead and make these changes and see what happens. First, we'll go to the hub VCN and create a new VCN route table for the DRG. We'll click Create. Let's call it DRG RT. Once this is created, let's go ahead inside and add the quad 0 static route and point it towards the third-party firewall. So target type IP address, the CIDR block is quad 0. Target selection is my firewall VNIC. Likewise, for the internal routing table within the VCN, we have to let it know how to route back towards these spokes by way of DRG. So let's add a route here, select target type dynamic routing gateway, and what I'm going to do is summarize the 192.168.0.0/16 block, which covers all 4 spoke VCNs. Next, we'll need to go back to the DRG and associate the DRG hub VCN route table with this VCN hub VCN route table. We'll select the hub VCN attachment, click on View Details, select Edit, Show Advanced Options, and within here, the VCN route table, we'll select Existing and associate it with the DRG RT. We'll click Save Changes, and once this association has been made, that quad 0 route, which was in the DRG hub VCN route table, is now propagated into the hub VCN and furthermore down into the spoke VCNs. So let's take a look at their DRG route tables. As we can see, the quad 0 has been now dynamically populated. Let's take a look at the spoke VCN DRG route table. And once again, it has been propagated here. So if we were to take a look at our compute instances, and there you go, they've started pinging. Next, we'll take a look at remote peering connections. Now that we've integrated the hub VCN, the next thing we'll take a look at is establishing a remote peering connection to a remote region so that we have connectivity from the spoke VCNs to the RPC. In this case, what we'll do is associate the remote peering connection with its own DRG route table and propagate from the RPC route table to the spoke VCN route tables and vice versa. First thing we'll need to do is let's create a DRG route table for the RPC connection. We'll call it RPC-RT. Once this is done, we'll create an import route distribution. Call it RPC. In here, what we're going to do is just import from spoke VCN1 and spoke VCN2 so we can test the connectivity from these 2 spokes to the remote region spokes. Give it a priority 1. With an attachment, we'll select the specific VCN, and we're going to do spoke VCN1 and spoke VCN2. Next, we'll go to the DRG route table and we'll associate the import list we just created with the RPC route table. So we'll click on View Details, click Edit, we'll enable Import Route Distribution, and we'll select RPC, Save Changes. Now we're ready to establish the remote peering connection. In order to do this, we'll go to the Remote Peering Connections Attachment section under the Resources on the left-hand side, and we'll click Create Remote Peering Connection. We're going to create our remote peering connection towards Ashburn. So we'll give it a name, RPC to Ash. We'll create that connection. And once this connection comes up and is attached, we'll click on the actual remote peering connection to copy the OSIT value. We're going to need that in order to establish the adjacency from the Ashburn side towards San Jose. So this looks like it's been created. And once again, we'll copy the OSIT value and we'll navigate to our remote region. In our case, it's Ashburn. We'll select the DRG. And what I've done here is I've already configured a couple of spoke VCNs. Pretty much the default settings has been working with. They're both attached to the auto-generated VCN route tables, And in this case, once we create a remote peering connection, there's the second DRG route table labeled auto-generated DRG route table for RPC, VC, and IPSec attachments. In this case, we're just going to let it associate with the default route table. So let's create a new peering connection towards San Jose. So RPC to SJ. And we'll give it a moment for this thing to get created. Once it's attached, we can click on the RPC name and select Establish Connection. And the region we want to connect to is San Jose. And the OSIT value that we just copied, we'll paste into here and we'll click on Establish Connection. This will take a few moments to complete, and once the peer status isn't available, we can proceed. Once the remote peering connection has been peered, we should be able to take a look at the route tables to see that both regions are learning each other's CIDRs respectively. Let's go back to the DRG, and let's take a quick look at the DRG route tables for the VCN attachments. If you recall, the VCN attachments are matching on anything, so we should now learn the subnets and CIDRs from the San Jose region. So do a get all routes. Perfect. So the 172.16 address range are our local spoke VCN1 and VCN2 attachments. The 192.168 ranges are everything we're learning from the remote peering connection. Likewise, the default route we're also learning from the remote peering connection. If you recall, the default route was being advertised from the hub VCN route table, and any route that's in the VCN route table and is also associated with a DRG route table will be further propagated dynamically throughout the DRG environment. Let's take a quick look at our San Jose side to compare the route tables. And specifically, what we'd like to do is take a quick look at the VCN attached route tables to ensure that they're learning the remote peering CIDRs. What we see here are 4 CIDRs or subnets that are being learned by way of RPC with a next hop towards Ashburn. With this said, we should now be able to go back to our compute instances in San Jose and ping the remote region compute instances. And there you have it. Spoke VCN1 is able to ping Spoke VCN1. Spoke VCN2 is able to ping Spoke VCN2. We should also be able to ping the other compute instance from the other Spoke VCNs from the local Spoke VCNs as well. So for example, Spoke VCN1 should be able to ping Spoke VCN2 in the remote region, and Spoke VCN2 in the local region should be able to ping Spoke VCN1 in the remote region as well. There you have it. Both local Spoke VCNs can reach the remote Spoke VCNs and vice versa. I'm going to break out of this. If we did want to segregate this traffic further, we could establish another RPC connection from San Jose to Ashburn and terminate both RPCs into their own, yet again independent, DRG route tables, and further propagate those to and from the Spoke VCNs, so as long as we terminate the Spoke VCNs into their own route tables as well. For our next step, we're going to create an IPSec tunnel and associate it with its own route table and propagate to and from the Spoke DRG route tables to the IPSec DRG route table, so we can have reachability between the on-premise network and the Spoke VCNs. First thing we'll need to do is create that IPSec tunnel. Now we have plenty of videos on our YouTube channel on how to create IPSec tunnels from a variety of vendors. I've already pre-configured this IPSec tunnel in the interest of time. What we'll do is we'll create a new DRG route table and import list, and we'll import to and from the Spoke VCN to the IPSec tunnel and test connectivity. So the first thing we'll do is we'll create that import route distribution for the IPSec tunnel. And for this, what we'll do is import just the Spoke VCN1 and Spoke VCN2, because this is what the IPSec tunnel will need reachability towards. So we'll go ahead and create that. Next, we'll create a DRG route table for the IPSec tunnel. And here, what we can do is we can associate that import route distribution as we're creating the DRG route table. We can select import route distribution, select the appropriate one, and click DRG route table. Previously, we've done this by editing the DRG route table and updating the settings from within there. And once this is provisioned, we'll go ahead and attach the IPSec tunnels to this DRG route table. So once an IPSec tunnel gets created, it automatically gets associated with the DRG you select. In this case, I've selected our demo DRG, and I've only brought up one of the two tunnel endpoints. We provide two tunnel endpoints by default for resiliency, but for the purposes of this demo, we'll just leverage one of the tunnels. So here, we'll select tunnel 1, click on Edit, and assign the appropriate route table. Let's click Save Changes. Now let's go take a quick look at this route table to see what it looks like. So from an IPsec's perspective, we can see we are learning the spoke VCN1 and VCN2 CIDRs. Since we are learning these dynamically, and since the IPsec tunnel has BGP peer configured with it, these routes will automatically be announced towards our remote CPE device. Any dynamically learned route will by nature be advertised to the remote CPE device. So let's take a quick look at our systems to see if we have reachability. Perfect. On the left-hand side, we have our San Jose compute instance. On the right-hand side, we have our remote CPE host, and we can see both are reachable. So let's break out of this. And if we did a trace route, we could see we're going through the tunnel. Now this looks great, but what if the tunnel between the remote CPE device and San Jose was to go down? Could we leverage the RPC connection between San Jose and Ashburn in order to leverage the OCI backbone for reachability? We certainly could, but this would also require that the remote CPE device has a tunnel built towards the Ashburn region. With this said, I've already configured a tunnel between the remote CPE device and the Ashburn region. Let's disable the tunnel between the remote CPE device and the San Jose region to see if we have reachability. Prior to doing that, let's start our pings to see what happens. And as we can see, the pings have stopped. And the reason for this is because each region is currently advertising its own CIDR towards the CPE device. The remote region CIDRs are still not advertised across the RPC connection towards the IPsec tunnels. So what we'll need to do to achieve routing to a remote region through the OCI backbone is import from the remote peering connection DRG route table and the IPsec DRG route table accordingly, as such. So the first thing we'll do is we'll navigate towards the Ashburn region. Once we get this configured, we'll do the same thing on the San Jose region. The first thing we'll do is we'll create an import route distribution list for the IPsec tunnel and a separate DRG route table for the IPsec tunnel, just like we did in the San Jose region. So we'll call this IPsec. And again, we want to import from both spoke VCNs In addition, we want to import from the RPC as well. Next, we'll create the DRG route table. And we'll click on the Show Advanced Options. And here, once again, we'll associate it with the corresponding import route distribution. And once this is provisioned, we'll go ahead and associate the IPSec tunnel attachments with this new IPSec route table. And we'll select tunnel 1 since it's the only one that's up. Select IPSec RT and we'll click Save Changes. And that's great. So let's go back and take a look at the RPC route table and the IPSec route table. From the IPSec route table perspective, we could see that the IPSec tunnel knows how to reach both regions' CIDRs. From the RPC route table perspective, we could see we can reach the local spoke VCNs. However, the RPC still does not know about the 10.0.0/8 route from the IPSec tunnel. So we'll need to further add an IPSec tunnel import to this RPC route table or the RPC distribution list. So let's go ahead and add that. This time on the RPC, we want to add one more statement to import from tunnel 1. Let's go back and take a look at the DRG route tables now. From an RPC route table perspective, notice now we are learning the 10.0.0/8 from the IPSec tunnel. Since this is a dynamically learned route, the remote peering connection route table will announce this 10.0.0/8 route towards the San Jose region. So in the San Jose region, RPC route table, we should see a 10.0.0/8 being learned now. So let's hop over there. It doesn't look like we're learning the 10.0.0/8 yet. And the reason why, the import list for the RPC will need to be modified. So here, we'll go ahead and add a third statement to import from the RPC. And we'll need to add a fourth statement to import from the IPSec tunnel that's terminating into San Jose. Let's click Save. Now let's go take a look at these route tables once again. So if we were to take a look at the RPC route table, here we can see we're learning the 10.0.0/8 in addition to the remote CIDRs. Let's close this. Let's go take a look at the IPSec route table. And once again, we're only learning these CIDRs. So what we'll need to do is in the IPSec import route distribution list, we'll need to import from the RPC attachment. Once we import from the RPC attachment, we'll see the 10.0.0/8 and the 172 CIDR being dynamically learned here, and this will allow us to announce these routes through BGP across the tunnel. So we'll add a third statement here, specifically remote peering connection. Save. Let's go back and take a quick look at the DRG route table for IPSec one last time. And there you have it. We have the 10.0.0/8 in addition to the 172.16s and the local region CIDRs as well. So let's go back to our device, and you can see that after quite some time, we did achieve reachability. Not only that, if we were to take a look at the round trip times, notice they're 140 some odd milliseconds now. Previously, they were about 40 milliseconds. So what if I was to re-enable that tunnel right now? Let's see what happens. And the tunnel's being enabled now. And there you have it. We could see routing has converged and we're back down to for about 40 milliseconds. So this is the way to achieve redundancy through OCI backbone to remote regions if your connectivity towards that region happens to go down. What if we wanted to further segregate the traffic from all the spoke VCNs to and from each other? In order to do this, we'll need to associate the spoke VCNs with their own DRG route table and propagate from the hub VCN route table to the spoke DRG route tables respectively. Prior to doing this, let's do a quick trace route to see what the traffic flow looks like between the spoke VCNs currently. As we can see, the first hop is the DRG and the second hop is the remote system itself. Let's go back into the console. Now, in order to get this started, what I've done is I've pre-configured the import route distributions and the DRG route tables for the spoke VCNs, since we've done this several times already. Let's take a quick look at what the import route distributions look like for spoke VCN 1 and 2. These are very simple. It's a single statement, essentially matching the hub VCN. Let's take a look at spoke VCN 2. Likewise, it's a single statement matching only the hub VCN. And for the hub VCN, we're still importing from all the spoke VCNs with this match all statement. Let's take a look at the DRG route tables and what they look like. So for spoke VCN 1, we are now only learning a default route and of course the hub VCN siders and subnets as well. Prior to this, when they were in the common route table, we were learning all of the routes from all spoke VCNs. So let's take a look at the spoke VCN 2 route table as well. And this is the same, a single default route with the hub VCN siders. So the last step we'll need to do is associate these route tables with the VCN attachments. So let's go to spoke VCN 1, let's view the details, click Edit. Under Show Advanced Options, let's associate it with the spoke VCN 1 DRG route table, and we'll do the same for spoke VCN 2. View Details, Edit, under Advanced Options, spoke VCN 2 route table. We'll click Save Changes. Let's go back to the compute instances and do one more trace route. Notice the second hop now is 192.168.0.22 from both sides. If you recall, this was the private IP we used to send traffic towards our third-party firewall. This essentially tells us we are navigating through the DRG through the third-party firewall prior to reaching the destination compute nodes. We've discussed a lot of concepts and technologies related to DRG, and we've had a chance to implement this throughout the demo. I hope you've enjoyed this demo. Thank you.